Let's try to work a very simple solution for this problem. So this problem says a man is running on a horizontal road at 8 kilometers per hour speed, and the rain is falling vertically as it appears to him, basically. And he increases his speed to 12 kilometers per hour, and he finds, that's an important word, that the drops make an angle of 30 degrees with the vertical. Now what we need to find is the speed and direction of the rain with respect to the ground. Okay, so the key point here is that we need to find the speed of the rain with respect to the ground. And what does that mean? That means the speed of the rain as it is going to appear to someone who is standing on the ground, and not to the man who's running. So in this case, what is happening is the guy is running at a speed of 8 kilometer per hour, and to this guy it appears that the rain is coming down in a vertical direction. And then what happens is he speeds up, so he decides to go fast, and as a result what happens is the rain appears to him that it is falling in a angle of 30 degrees with the vertical. And what we need to find is the speed of the rain. So how does this problem, how do we explain this? First of all, it's a problem of two different frames. There is a frame of reference which can be attached to the ground, and there is a frame of reference which can be attached to the man. And these both are different frame of reference, and the way any object would appear in any frame is unique to it. So in a scenario where you have multiple frames of reference and some observations are given, the velocity as it would be observed from the ground, and this is VRG, or velocity of rain with respect to ground, can be summed up as velocity of rain as observed by the man plus velocity of man and as observed from the ground. Now we have to understand that velocity of rain with respect to the ground is going to be same in both the scenarios. What will be different is velocity of the rain with respect to the man, because in one case it appears to the man as to be falling vertically, and in the second it is appearing to be falling in a certain at an angle of 30 degrees from vertical, even though the rain may be falling in a certain way. And the other part is the speed of the man with respect to the ground is also changing. In one first case it is 8, and in the second case it is 12 kilometer per hour. Now in order to find this value, let's call this value as V, since it's going to be the same in both cases. Velocity of rain with respect to the ground is going to be the same in both the cases. And let's draw vector diagrams of both the scenarios. Let's say this is scenario 1 and this is scenario 2. So vector diagram of scenario 1 looks like to be, so this is the guy who's running at 8 kilometer per hour, and to him, and let's say this is the velocity as it appears to him, velocity of rain with respect to the m. or the man in the first case. So this is the final vector as it would be observed by the man. So in order, the vector rule of addition says if this is the final vector, then it has to be obtained in this manner that when you add two vectors, that should give us the resultant vector. So if this is the speed, if this is the vector for the speed of man, and this is the vector for the speed of rain, the actual rain, then this is how we would be able to get the resultant vector as it would be observed. And here this is, since it is falling vertically, it will be making an angle 90 degree, or this would be perpendicular. And let's say this velocity or the speed of the rain is at an angle theta with the vertical. So that's the scenario one for us. So what we can say from this first vector diagram is that the component of this velocity along the x-axis should be equal to the velocity of the man. So what we can put here is, completing this vector diagram like this, so the magnitude of this line, and let's say this point is A, this point is B, this point is C, and this point is D, then CD is equal to AB in magnitude. So that means V sine theta is equal to 8 kilometer per hour. So that's like our first equation, and this is something we would be using subsequently when we discuss the scenario 2. And what does the scenario 2 look like? In this case, his speed is more than the first scenario, and let's say this is 12 km per hour, and the rain comes out at 30 degrees from the vertical. And this vector is velocity of rain with respect to man in the second scenario, and this will be different than Vrm1 in the first scenario. And if we complete the vector diagram, the speed and direction of the rain with respect to the ground is not changing, it's still the same. So if we complete the vector diagram, so this is how it is, and this is V, and again this is theta, same as above. Now in this, if we want to find our way around, there are two things we can look at. That the component of this vector along the horizontal and the component of this vector along the horizontal, when added in magnitude, they should give us this velocity. That said, this angle is going to be 60 and this angle is going to be 90 minus theta. Therefore, Vrm2 cos 60 plus V cos 90 minus theta is equal to 12. That means Vrm2 into 1 by 2 plus V sine theta is equal to 12. So that's our second equation. And another thing is that the vertical component of this vector and this vector will be the same. implying VRM2 sine 60 is equal to V sine 90 minus theta, or VRM2 into root 3 by 2 is equal to V cos theta. That's equation number 3. Alright. So from these, what we can find out is I can express this value as VRM2 is equal to 2V cos theta over root 3. That's my equation 4. And I can substitute this value in here, and that way I would be able to get rid of VRM2, because it's a relative, it's a velocity with respect to the man, and this is something which is not of interest to us at this point. We are more interested in finding V and the angle of the rain with respect to the ground. So VRM2, when we substitute here, we get 2V cos theta over root 3 into half plus V sin theta is equal to 12. That means if we take V as common and this 2 can get cancelled, we get V brackets cos theta over root 3 plus sin theta is equal to 12. That's equation 5. Now if you look closely, equation 5 and equation 1, both of them have V and theta as a variable. Now we have two equations now. Let's divide this first equation by the second equation. So what does that give us? Dividing 1 by 5. So we get V sin theta over V cos theta over root 3 plus sin theta is equal to 8 over 12. Now these get cancelled, and now dividing both numerator and denominator by cos theta, because usually the angle of a vector is given as a ratio tan theta. So that's the reason I divide numerator and denominator by cos theta, so that I can get a tan theta over 1 over root 3 plus tan theta is equal to 2 by 3 on simplification. And now cross multiplying and solving, we get 3 tan theta is equal to 2 over root 3 plus 2 tan theta, or tan theta is equal to 2 over root 3. That's one of the values, or this is the angle at which the rain is falling from the ground. Now to find V, we had V sin theta is equal to 8, or V is equal to 8 cosec theta, and there is a relation by which you can relate. If tan theta is 2 over root 3, assuming it to be a acute angle, now this value will be square root of 2 square plus 3, which is equal to square root of 7. So we can get cosec theta would be root 7 over 2, or 8 into root 7 over 2, or 4 root 7 kilometer per hour. And that's how we would approach this problem. There are multiple ways of doing it, but I thought really we need to break it down in a simple manner and be able to construct it step by step. I hope you like it, and if you like me to create more content or be able to guide you with more problems related to maths or physics, just do write me up in the comments and I'll be more than happy. Thank you.